Welcome to section 12.15. All right, gentle people, in this lecture, we're going to go over some periodic trends. So the best way to go about this is to ask you guys some questions. So start with this first quiz question. All right, so what I want to do is I want to go down the periodic table. So if I go down the periodic table, what I know is I go from n equals 1, n equals 2, n equals 3, and what I know, n is going to be the energy of the electron. And the higher the energy, the further the electron is from the nucleus. So as I go down the periodic table, what I will see is my atom adds another shell and gets bigger and bigger and bigger. So as I go down the periodic table, my atomic size is going to increase. So let's do our next quiz question. So gentle people, this one's a little tricky to understand. As I go across my periodic table, what I'm doing is I'm increasing the amount of protons I have. I'm also increasing the number of electrons I have. Now you might think that I'm going to go ahead and increase the size if I add more stuff. But what you have to take into account is the effect of shielding. So if I look at my periodic table, what I'm going to have is I'm going to have a layer of my core electrons. And let's say that I'm in the first column of my periodic table, and then I'm going to have one valence electron. If I move over, I'm going to have the same core electrons. I'm going to have two valence electrons because I'm in the second column. So if I want to go ahead and take a look at the Z effective on these electrons, that's going to be Z minus my shielding. But what you will notice here is that in both of these cases, my core is going to be the same. So my shielding is the same, however, my Z is going to increase because I've added more protons. So what happens is my Z effective is going to go up. So as I move across the periodic table, my Z effective is going to go up, but my shielding stays the same. If that's the case, the valence electrons are going to feel the pull of the nucleus more and more as I go from left to right. And if those electrons are feeling more of the nucleus, they're going to be pulled in tighter. And so as I go across the periodic table, I'm going to decrease in size. So if you guys wanted a pictorial representation of the atomic radii, here's the picture. You guys can see as I go down the periodic table, atoms get bigger, and as I go from left to right across the periodic table, my atoms get smaller and smaller. So taking those two factors into account, which of these elements has the smallest atomic radius? Okay, gentle people, so if we put those two factors together, top right-hand corner of the periodic table has the smallest atoms. And the bottom left-hand corner of the periodic table has the biggest atoms. So what I want is the element that is the top right-hand most element. So in this case, chlorine is the topmost rightmost element from this list. So to continue with our discussion on periodic tens, let's go ahead and talk about ionization energy. So an ionization energy, I'm talking about a specific reaction. I'm going to take an element in the gas phase, and I'm going to pluck off an electron from that element. So to give you an example, if I take sodium and I separate one electron, leaving Na+, this is called the first ionization energy. And that is the energy to remove that one electron. Now there's something called the second ionization energy, and what that is if I take that Na+ and remove that second electron. So note the second ionization energy, I'm starting from the products of my first ionization energy. So let's take a look at the trends of ionization energy. As I go down the periodic table, what you guys will see is it takes less energy to remove an electron. And that should make sense to you because as I go down the periodic table, I'm getting bigger and bigger. So as I go down the periodic table, what you guys will notice, there are electrons that are further and further away from the nucleus. If they're further and further away from the nucleus is going to have a hard time holding it, and so that's why it gets easier to pluck off an electron as I go down the periodic table. Or it's going to take less energy as I go lower and lower on the periodic table. The same is going to hold true as I go from left to right. Because the atoms are getting smaller, they are closer to the nucleus, and so that's why it's harder to pluck off electrons from the right-hand side of the periodic table compared to the left-hand side. So the general trend is that as you go from left to right, it's going to take more energy. Now, one thing to note about ionization energies is that valence electrons are really easy to remove. So if you compare ionization energies, you'll notice that the ionization energies are in the hundreds. But as soon as you pop into core electrons, you get this huge jump into multiple thousands. And what that is saying to you is that removing core electrons are extremely hard. The valence electrons that you guys have available to you, these are relatively easy compared to the core electrons in the atom. The next periodic trend that I want to talk about is electron affinity. Now, electron affinity has to do with the reaction where I take an element and I try to stick on an electron to that element. So to give you an example, I can take chlorine in the gaseous phase. I'm going to try to stick on or tack on an electron to make the chloride ion. Now, what you should note is that if you guys go ahead and stick an electron onto an atom, it is going to release energy. So the greater release of energy, the easier it is to stick on that electron. So let's go ahead and take a look at some trends. As I go up the periodic table, what I will see is the energy released from the atom is going to be more and more when I try to stick on an electron. And this should make sense to you because if I put that electron next to that proton, this is a favorable interaction. And so that is going to release energy. The closer that electron gets to that nucleus, the more energy it's going to release. And again, to remind you, as I go up the periodic table, these are going to be my smaller elements compared to the big ones right here, so the electron can get much closer. The same is going to happen as I go from left to right on the periodic table. As I go from left to right on the periodic table, what you guys will see is I will release more and more energy. So here you guys will see the summary of the general trends on the periodic table for atomic radius, first ionization energy, and electron affinity. Now, these are the general trends that you see on the periodic table. What you might have noticed is there are some little exceptions and some little nuances. The first thing you might have noticed is if you look at ionization energy, what you would see is that this column that contains nitrogen has a higher ionization energy than the column that contains oxygen. Let's take a look at why there's a small break in this trend. So here's the electronic configuration of nitrogen and oxygen. And normally what you would think is that as you go from left to right, it becomes harder to remove an electron. But it turns out that oxygen is easier than nitrogen. And if you look at the electronic configuration, you can see why. So if I remove an electron from nitrogen, Well, any old electron will do. There's nothing special. However, for oxygen, I can remove a paired electron. And it turns out that when we start pairing electrons, it becomes easier to remove that paired electrons. That's because these two electrons are in the same vicinity, they're repelling each other, and so it's slightly easier to remove a paired electron than an unpaired electron. This also explains the discrepancy in the electron affinity trend. What you will notice is nitrogen has a very low affinity for electrons. And going back to our picture, you can see why. So remember, electron affinity means I want to stick a new electron into my atom. And so for something like carbon, which has an empty spot, it's fine. You can stick on an electron and it releases energy. However, for nitrogen, if I want to stick in an electron, I have to begin pairing up electrons for nitrogen. So I don't get as much energy back out because I'm trying to force an electron into a spot where another electron is currently residing. And so the take-home message is, yes, there are general trends in the periodic table, and if you have these small deviations, you can explain them using the electron configuration. I hope this made sense, and remember to stay safe, Chem 1A.